Okay. Welcome everyone for our Institute Colloquium series, and today we have our own Professor T.R. Govindarajan. So all of you know him very well, so I don't need to introduce, and I will give the stage to him so that he can start. Yeah.
Okay, thank you very much. It was kind of a provocative title I thought about, and I gave this thing RRR. So don't expect me to do any dance of the film here, but I'll try to tell something about Ramanujan. Now, the reason I chose this particular date and mentioned to Sayanthan, in fact, about during coffee time, came as a private discussion, and also Namani, etc. 26th is the death anniversary of Ramanujan today, and in principle many places where they think great about greatest mathematician this place has, the country has produced, or from this region, so they remember on 2 days, one is birth anniversary and death anniversary, and they do talk about it. In fact, I have been getting a lot of Facebook messages saying that we should remember this man, etc., etc. So I thought there will be some mathematics talk. So I offered this thing more as a provocation, so that for physics faculty, essentially physics colloquium. Then apparently after some discussions they decided that they will have it as an institute colloquium, because it might be of general interest also. So that is why I happened to talk about this. Okay. So this is about Ramanujan, his regularization and renormalization. You all know Ramanujan, and what is the connection to regularization and renormalization is what I am going to speak about. And of course, there is some brief thing about which I had to mention. Genius was born on December 22nd, 1887. You can have birth anniversary talks also. And he died at the age of 32 on 26th April 1920. And within this time, short duration, 32 years, and several kids, childhood days, etc., if you subtract, he essentially had about something like 10 to 12 years. And in that 12 years, he did extraordinary work and amazing levels of achievement. And he can easily be called the man who knew the meaning of infinity. Okay? The meaning of the word infinity itself, because he has used it in several occasions to the surprise, and I will try to point out actually 2 events. That's my goal, and which is connected to physics. So he lived in the small traditional place, in a place called Kumbakonam, in the street Sarangavani East Sanadi Street in Kumbakonam. And I'm interested in this as more as a personal thing, because I also lived in the same street. And he went to a school called Town High School Kumbakonam in the center, which was it's a very, very old school. It was started in 1864. And that's why he could go in the year something like 1897 or something like that, or that time. And I also happened to go to the same school 70 years later. So that's my personal attachment to that. And before many of you have heard of the greatness of Ramanujan, the school always talked about Ramanujan. In fact, they always had a Ramanujan hall in that place, even when I was a student there about 60 years back. And that is amazing, because that is the greatest thing they can be proud of, and they were actually, no doubt. That family home where he lived is a museum now, held by Shastra University. In fact, our Srinivas Rao was also involved in that. And understanding infinity in physics is very crucial. We have to understand the meaning of infinity, because everywhere there is some infinity coming up. we have to understand it in clear terms. And it looked like if Ramanujan had, instead of this, or in addition to the book of car, if he had got hold of some other book also, doing physics problems, Loney and other things, dynamics problems, etc., he might have become a great physicist, where some of the things which he intuitively did will have some resonance. And the way I point out, it looks like he might have been a great successful theoretical physicist also. So I'm going to talk about some of these things, one or two of this in this context. So this is the home where he lived in the Sarangamani Sanai Street, East Sarangamani Sanai Street. In front of this, very close to that, about 100 meters away, there is a famous temple. And that is his usual place where all children, all adults, etc., they roam around and whatever knowledge they can, that probably get it. And I also used to do it. Now, I have one more thing to say. Around 2012, when it was 125th birth anniversary, December 22nd, I was invited to the school, because I also from the same school, Town High School, they wanted me to speak to the students and also take part in their 125th year. So as old boy, old student of that school, I was invited. And very interestingly, this is a meeting which I attended. I'm speaking, and you can identify a couple of more people who were from this institute on the back. They had come to Tiruvarur Central University, which was also holding a meeting exactly in the same place. And Srinivas was there, etc. And we were speaking. This is a school in which I spoke, and Srinivas also spoke, etc. This is I do go there on and off, and I'm in touch with that school, the principal, etc. And I do go there and sometimes take classes for the students about science in general. And I will tell, I did give about half an hour talk to the students on that day. This is a public talk, but to the students specifically, I spoke about some mathematics, a little bit just to provoke them, and this is one of the things I'm going to talk about. Okay, the way to understand his contribution, just I will spend a couple of slides on the greatness of Ramanujan, and then I will focus on what I want to tell, is to look at the number of terms named after him. Wolfram's encyclopedia lists about 27 terms named after him. There has Ramanujan series, Ramanujan number, Ramanujan function, etc., etc. And approximately, his name is associated with some 200 further items where many people will be involved also. So that is a kind of greatness which he is maintaining. Now, if you really want to compare, of course, the great people like Euler has 71 terms, Gauss has 48 terms, Hilbert is 33, Fermat is 32, and Riemann is 31, and you have our Ramanujan himself is in 27, followed by Cauchy, Dirichlet, Jacobi, Weierstrass, all those people who are. So he wrote 32 high-impact papers in Cambridge after his visit to Cambridge, and 7 of them in collaboration with Harding. And of course, on all the 32, there is no point in talking about citation, etc. When citation has no meaning, when you reach that kind of level, it's like saying, what is the citation of Schrodinger's equation? There's no meaning at all. It is some kind of Vedas book kind of thing. So that is the greatness. And he became FRS in 1918, and one of the youngest to achieve. In 1912, Ramanujan sent letters to several mathematicians in England seeking support for recognition of his work. He didn't want to go there, but he wanted to know whether what he is doing is important, good, and comments by them. All of them ignored except one, which is G.H. Hardy. And G.H. Hardy and Littlewood in Cambridge at the time, more or less holding the British mathematics thing, because at that time, France and Germany had such a control over international maths, and Britain was nowhere near it, and these are the two people who were holding fort in that. And in that letter, Hardy, he received 120 equations. Apart from the first page, which is introducing himself, I beg to introduce myself, kind of statement. And after that followed some 7, 9 or 10 pages on 120 equations, and of course no proof. And some of them were known to him, some were slightly incorrect, and the rest were extraordinary. He recognized immediately such formulae could not have been written by a person without deep understanding in mathematics. That was his immediate conclusion. He even said, some of the equations defeated me completely. I had never seen anything in the least like them before. They must be correct, because it is even difficult to cook them up. How do you cook up such equation? So that is the kind of remark which he made. So he invited him to come to Cambridge. And the rest of the developments, this is in 1914, until 1920, when he had got this TB, 1919 or so, till 1920, everything is now a movie, so I don't have to tell more about it. His research in partitioning and its approximate formula contained in miraculous number pi. Ramanujan was fascinated by this number, and he looked at it from different angles and postulated several series, and he finally landed up in one series, which is probably fastest algorithm for pi. Now this equation number 1, which I have written down, it's an infinite series. Now you take the first term, it gives you pi to 8th decimal place. And you take the second term, add it, and it gives you up to 16th decimal place. Take the third term, it gives you up to 24th decimal place. It just took about 10 terms if you take, you will get up to million terms which are accurate for pi. Now, how did he guess that kind of a thing is even now mysterious. And Hardy called it as mingled set of arguments coupled with intuition. You don't know where it came from, which Ramanujan himself could not describe, because he has done all these things in his slate and board, and whenever he reached something, he wrote it down in his famous notebooks, and only the formula, final formula was there, and he even corrected them as he improved it much later. So this is the level at which his intuition was working. So this is that famous equation which I gave you in the previous slide, and the first term is what I have written down. We always tell in the schools and classes 22 by 7, okay, for pi. Now if you take this, you will get up to some 16th decimal or 10th decimal for pi. This is a thing here, okay. So this is a paper, in fact somebody has talked about this thing, where they have used it to compute pi to billion digits. And this is that equation which I have there, is there in the last, okay. So this is something which I took, and then they have used it also to understand it better. Okay, so that is as far as the greatness of Ramanujan is concerned. I'm going to focus on the real issue which I wanted to point out. Now he wrote in his letter to Hardy, okay, he wrote in his letter to Hardy, there are two series which are there. And one is the first one, 1 plus 2 plus 3 plus 4 up to infinity is minus 1 by 12. And the next one is 1 plus 2 cube plus 3 cube plus 4 cube, which is 1 plus 8 plus 27 plus 64 up to infinity is 1 by 120. These two equations are there in that famous 900 equations which he wrote, and the 10 pages, etc. You will find it. In fact, there are so many equations. I just took only 2 of them, these 2 equations. These strange relations were source of fascination for many amateurs who talk about it. In fact, I have also given some YouTube talks on this, and with millions of views on this, okay. They are provocative equations because obviously it is divergent series. And how is he getting and that to adding all the positive numbers, he gets a negative number. minus 1 by 12. Okay? So obviously we have to tell the meaning of the summation, the sigma, or equal to, what you want to call it as equal to. Okay? And that's why we should use it as equal to with an R on top, which is what I have indicated here. Okay, so this is in his own handwriting. 1 plus 2 plus 3 plus 4, and C is equal to minus 1 by 12, 1 cube plus 2 cube plus 3 cube. This is actually taken from his actual letter. Okay, and he has given some kind of a remark in a later notebook, which is there, and C is equal to minus 1 by 12 can be seen at the end. Okay, and you can see some where there was some clue and couple of equations, and I will try to tell, because I use some of those things in my own lecture which are incorrect. Okay, so this is the thing. Now the second letter he wrote after maybe a month or so. I'm very much gratified on perusing your old first letter. I was expecting a reply from you similar to the one which a mathematics professor of London wrote asking me to study carefully Bromwich infinite series and not fall into the pitfalls of divergent series, because that is what is the problem. I told him that the sum of an infinite number of terms of the series 1 plus 2 plus 3 plus 4 is equal to minus 1 by 12 under my theory. This is what he writes. If I tell you that this, you will at once point out to me the lunatic asylum as my goal. I dilate on this simply to convince you that you will not be able to follow my methods of proof if I indicate the lines on which I proceed in a single letter. Obviously, he had something else in his mind, and it cannot be expressed in a letter. That's what he was trying to tell. But it is not a serious thing for a person like G.H. Hardy, and I will explain why it is so. So I was asked to speak to the students in the town high school when I went there. So I gave a proof, and as I have indicated, it's a fake proof. So I call S as 1 plus 2 plus 3 plus 4. I multiply that by 4S, 4 times. So 1 will become 4, 2 will become 8, 3 will become 12, 4 will become 16, etc. I just put a 0 in between. So I subtract S minus 4S will give me minus 3S. And that is, you can say it is 1, and there is a 2, and then the 4, which is subtracted, will give you minus 2. And then there is a 3 plus 3, and then the 4 and 8 will give you minus 4. So it will become alternate. 1 minus 2 plus 3 minus 4 plus 5. This series is also known as Euler's series. So minus 3S is equal to alternate series of 1 minus 2 plus 3 minus 4, etc., etc. Then I have to tell the students of Town High School who didn't have any other thing, so I cannot do more than addition subtraction. So I multiplied this 3S by 4. So I'll get 12S, minus 12S. So which means I have to write the series 4 times. I have to write the series 4 times. So I write 1 minus 2 plus 3 minus 4 plus 5 minus 6. Second time I write it one step below the 2. 1 minus 2 plus 3 minus 4 plus 5. Third time again I write it below that, which is 1 minus 2 plus 3. Fourth time I write on the third term, 1 minus 2 plus 3. Now you can add vertically all the numbers. You will get 1 plus 0 plus 0 plus 0. So minus 12S is equal to 1, and the answer is S is equal to minus 1 by 12. So that is a proof. Obviously the proof is not correct. It uses a lot of incorrect usage of the words, addition of infinite series, etc. But the answer seems to be okay, correct. So this is the basis. Now Hardy was aware of what is known as Riemann zeta function, a little more serious, which is 1 by n power z, where zeta of z, which is well known, which is this thing. And Riemann established the analytic continuation. I will mention some of these things of this series, of this function. And Hardy immediately saw this zeta of -1 and zeta of -3, because that's what he is trying to do. Incidentally, nobody has actually worked out what is zeta of -1 and zeta of -3 before at that time. So he asked Littlewood to do a little calculation and find what is zeta of -1 and zeta of -3, and found out that is exactly -1/12 and that number. Okay? So he immediately understood what he has done is he has converted the series into limit of z going to -1 of this zeta function, an analytically continued thing, and this is the answer. And interestingly, Riemann, like Ramanujan, lived in poverty, where he actually was not great in terms. Till Gauss gave him a job. Okay? Gauss gave him a job in Groningen, and he gave it. And he also suffered from TB like Ramanujan, and he died also at the very young age of 39. And of course, the difference is Riemann had education in outstanding mathematical institutions, Göttingen and Berlin, unlike Ramanujan. So he was very strict about his proofs. He was very extremely worried about the proofs, rigorous, and unlike the style of Ramanujan. And most important, Riemann was an expert in complex analysis, and Ramanujan was not. He probably didn't know at that time when he wrote all these things anything about complex analysis. And if zeta -1 and zeta -3 are the answers for this sum, which Hardy immediately understood, they were not the procedure by which Ramanujan went. So it is a mysterious thing. How did Ramanujan arrive at those numbers? And it cannot be the proof which I gave, because that is, even I know it is a fake proof. Okay? So this is the point. Ramanujan did not write down the proofs of the series, but interesting thing is you can look for clues or anything which is there in his thing. In his second notebook, which is called the Last Notebooks, okay, there are some 6 of them, Ramanujan's last notebooks. In the second notebook, he had written few more series, another series which can be considered as intermediate step. This equation is also mentioned in his letter to Hardy. In that letter, it is also mentioned. And that is there in last notebook also. And that series is that 1 minus 2 plus 3 minus 4, which is, people like Euler have actually given that value as 1/4 in some curious fashion. This is related to Dirichlet function eta of z, which is only the same series which I had with alternate positive and negative. It is 1/1 power z minus 2 power z plus 1/3 power z, etc. Now, if you have this definition, you can easily establish zeta of z is related to eta of z by that formula, which is there, equation 5, which is not very difficult to. So if you know the value of eta of z as 1/4, substitute z is equal to -1, you can easily get zeta of -1, which is what it was easy to follow. That is the kind of a thing. Okay. Now we have to go a little more beyond that. And what is it we have to do? We define a new function which is called z power n, which is 1/1 plus z square plus z cube. And then you can take this g of z, multiply by z, you will immediately find it as 1 plus, it is same as 1 plus z gz, with mod z is less than 1. From there you can easily understand my g of z is 1/1 minus z, with singularity at z is equal to 1. The series converges only for z less than 1, mod z less than 1, but the g of z is defined everywhere except at 1, where it is singular. That's the point. The complex function g of z is holomorphic in complex analysis terms, completely differentiable in C minus that 1, and therefore meromorphic in C, which implies that its analytic continuation from the disk to C minus 1 is unique. Hence, you can even get the series g of -1, which is 1 minus 1 plus 1 minus 1, etc. There is a name for that series, which is called Grandi series, which is equal to half. Okay, Grandi series, the value is half if you follow this kind of a summation. We can extend the above to gz square So you have to essentially take that and then multiply twice, which is not very difficult. You will get 1 plus 2z plus 3z square plus 4z cube, and is equal to g prime z, which is nothing but 1 by 1 minus z whole square. And from there you can get eta of minus 1 as 1 by 4 from that formula by substituting z is equal to minus 1. This is the same as we needed in the second series, that second one which was there. And one has to, we can say that whether did he go through this kind of a road, because he had written these equations also. Now other way is what we do in physics, which I'm going to explain a little more, is regularize the divergent series. This is the first time I'm trying to use the word regularization. So replace that with a function n f of n divided by capital N. That function f of x goes to 0 faster than the growth of the series n itself. So what you will have is you can take that thing and then find out the limit, what are the terms, which will turn out to be minus 1 by 12 plus order n square, capital N square. When if you take n is equal to infinity, which is what will give me, then you will find that divergent series is always there. So this is the one way of looking at. Ramanujan seems to have defined, this is a guess from his last notebooks, as mentioned in Gandelperger, and that book is available in our library. Ramanujan Summation of Divergent Series is the name of the book, and the lecture notes in mathematics, that is the title. So he wrote another series which is called R1 of Z, which is n minus z to the power n minus 1. Now if you take z is equal to minus 1 in this R1, it is the same series as R. Okay, it's easy to see. So if you take the limit, he knows this R1 of z because it is there in his notebook. He also knows about g of z because that is also there, which he has mentioned. So if you take g of z whole square minus R1, you will find it to be 1 by 4 minus r as a series, and then take z is equal to minus 1 in that, you will get this formula which is there, minus 4r is equal to some, from this thing, you will get 1 by 12. It looks like he was playing with this kind of a series, one after another, and he was able to isolate an infinite part. Okay, first of all, he was getting some finite series, doing the calculations, and then isolate the infinite part, remove it by another series, and then get a finite value. This seems to be the way in which he has been proceeding. In the series sigma n, each is a number. If it is promoted to n power minus z, where z is a complex variable, then one can manipulate in a more rigorous fashion. That's what Hardy would have done. The variable can be set to minus 1 later. So we will call in physics now that as a zeta function regularization. We call it zeta function regularization. And these are various zeta function formulas which are there and relation to eta of z. And these functions are true in all analytically continued regions where the series diverge. The actual series diverges. So that is the interesting part about it. So now there is a formula known as Euler-Maclaurin formula, which is sigma fn minus sigma the integral f of x dx, and then that formula can be worked out. It is there in many books. I'm not going to give that proof of that, which is in terms of Bernoulli's numbers b2n, and that fm n which is there in that bracket, okay, which is there in the bracket here, they're all derivatives of mth derivative of f of n, evaluated at n value. So the Bernoulli's numbers are b0 is equal to 1, b1 is equal to minus 2, b2 is 1 by 6. These numbers play a very important role, and this is what helped later understanding of this series also. Now, so far so good for the mathematics of what Ramanujan did, the two series which he wrote. He tried to understand it purely playing with the thing and then trying to remove the divergent part and getting a finite number out of it. So, okay, it's only a game. Okay, that's what we would have said. The above divergent series occurs in study of string theory in 26 dimensions, bosonic string, which people call. And the finite value minus 1 by 12 is very crucial input in understanding the theory. It is well known that number is utilized in understanding the theory, where the theory will become, string theory will become, bosonic string theory will become meaningful in 26 dimensions, then superstring theory will be meaningful in 10 dimensions, etc. All those things come because of some divergent series analytically continued, and this value is taken. It is uniformly true. Okay, that is what is the thing. Okay, but I will focus on very simple example, which also has experimental justification, unlike string theory. So unfortunately, there is no string theories here. I just wanted to make fun of them. But anyhow, this is what is a statement. And I'm going to give an example. So what is that example? That example is known as Casimir energy in the literature. Okay? Of course, there are other places where regularization and renormalization has been used. I will point out. But I wanted to do some simple calculation, which will be where these two series appear, explicitly appear. The effect, what is called Casimir effect, was predicted by the Dutch physicist Casimir in 1948, around the time of the successful quantum electrodynamics, which introduced the term regularization and renormalization. That is the kind of thing which they were playing with. Okay. I'm going to give a toy model of what is called massless scalar field. One doesn't need great understanding of quantum field theory in a big way. It's simply standing modes, which I'm going to work out. Now, what I'm going to have is in 1 dimension. You can later increase it to 3 dimensions, 3 plus 1 dimensions. So the scalar field is a scalar field phi in 1 dimension x, and the time is the time direction on a real line r. Now, there are some bound. I'm going to put a plane, a box at 0 and L. So beyond that, nothing is there. So you have the Dirichlet boundary condition that phi naught is 0, phi L is 0. So essentially, you are going to consider the wave equation for phi and solve it between them. This is what all the college students do as particle in a box problem, and the solutions are sin n pi by x by L or something like that. That's what will be the thing. So the equation to be solved is only d naught square minus dx square phi xt is equal to 0. I've taken, if I put m square phi in addition to that, it will be massive particle, but I've taken for our example without mass. We can Fourier expand the field phi and write down the same Hamiltonian, which is 9, equation number 9, and do the complete integral. Now, since the standing modes are discrete, and the discrete modes have, I have standing modes are n pi x by L should come, n pi x. There is a mistake here. And they actually vanish at x is equal to 0 and L. That's how it is fixed. And these are the modes, and they will have energy which are given by that n square term which is there, and each of this thing. And then you will find there is a 0 vacuum state. What is called vacuum state, because of the ordering which is there, there will be a term half n pi. So this is the next term. Standing modes contribute, each of them contribute half of that n pi by 2L for the vacuum energy, which is given by Hamiltonian, which is sigma n pi by L and then 1 by 2L, which is outside. So obviously that sigma n is coming here, and sigma n is actually going from 1 to infinity. Okay, that is what is the thing here. So immediately Ramanujan's mysterious series appears, and what is it we can do? And as physicists, what we do is we regularize it. And regularize it, as I mentioned earlier, n is replaced by n f n by L n, where f naught is 1, and it's a smooth function. N tending to infinity gives you if you take n to infinity, you will get back your original thing. That is what is required for our purpose. So a simple example of regularization will be e to the power n by ln, and then we can immediately work out n e power minus n ln as derivative of d by dn e power minus n by ln, and you will immediately see that first term is ln square, which is what you expect. You expect that because there is a quadratic n dependent, capital N thing, it's infinite value, and divergence will come when n tends to infinity, and that is ln square. And minus 1 by 12, that is a crucial number which Ramanujan obtained, and the rest of them are order 1 by ln, which n going to infinity, it will become 0. So we take the limit n tending to infinity, subtract the divergent contribution by subtracting L is the term which is coming from L is equal to infinity, and what you do is essentially you have the 0 L, and then you have put a bigger box which is of size L is equal to much larger, and then subtract this from that, then you will get L is equal to infinity terms are cancelled, and you will get the answer as, because of that minus 1 by 12, you have that potential is minus pi by 24 L square. Now what is the use of this thing is essentially, if you have in this dimension, one dimension, if you have the parallel plates, and if these are all some electromagnetic radiation which is there, no other force, no gravity, nothing, they are not even interacting, that there will be a force of attraction. If you take the gradient of that, there will be a force of attraction. Now that is a question which was proposed by Casimir in those days, and Ramanujan summation to obtain the finite value corresponds to two steps. First, regularize the sum to finite limit. Second, subtract the infinite volume limit of the vacuum energy, two terms, and the energy diverges in both finite and infinite interval, but the difference is finite, and that reflects the finite size effect, which is well defined. This is basically the idea of renormalization which we have been doing. I can explain this in QED and other places, but this example of a massless scalar field is very simple to understand, and what is called the QFT through counter terms, the subtracting that infinite volume limit, or bare mass if you want to call anything, is what we do as a counter term in this kind of example, and this is what is the thing. This process of regularization and renormalization has been successful in QED and provides successful measurement of, say, dipole moment of the electron, okay? Because this is after only doing such a subtraction, QED, we find the value of the dipole moment of electron, and it is accurate up to 10 power 9. It looks like arbitrarily you are doing some regularizing and subtraction, which is what physics intuition has been telling us to do, and getting the thing, and the answer seems to be experimentally completely correct. And the factors which I have used, that minus 1 by 12, etc., are very important there. It is a force between Dirichlet boundaries which are obtained by in the example here. The gradient of the energy, potential energy, gives the force between the plates. Now this is, I did it in one dimension. I can do it in 3 dimensions. In one dimension, what the series which I get is sigma n, okay? Now if you do it in 3 dimensions, let us assume at that time, this is what Casimir did, conducting plates of rectangular shape of area A, okay, the 2 plates, because this is in 3 dimensions, and you have 2 plates of infinite, very large area, and the root A, the size, should be much, much larger than the L, the distance between the 2 plates, and you do the calculation. Again, it is a very simple, straightforward, same calculation which we did, we have to only manipulate. So what we do is we look for the pressure on the walls. What is the pressure? Find out the energy. Pressure is force by area, and find the energy. Gradient of the energy will give you the force, dE by dL, divided by area, which is I have mentioned here, and it's very easy to calculate that part. And if you do that, the pressure will turn out to be minus pi square by 8L power 4 and zeta of minus 3. That zeta of minus 3 is only, I have replaced it, what you get is sigma n cube. Okay? Sigma n cube is what you get, and you get that pressure. Now you can ask the question, is it a good thing? Answer is, you do experiment. You keep a plate, very short distance, and try to find out whether there is a pressure. Okay? Now these are all neutral plates, so you don't expect any force between them, etc. And gravity between the two plates is too small to affect. And is there a force between them? That can be measured experimentally. And there is a pressure of this nature, which is mentioned here. But I'll tell you little complications which can be there. In this context, Ramanujan summation sigma n cube appears, and that's why we get this pressure as, after substituting the value of zeta of minus 3, minus pi square by 240 L to the power 4. Now the actual experiment when you try to do, we have to be careful, because the surface which you have may not be smooth. Various other factors will be there, and there could be finite temperature. I did everything in 0 temperature. There should be finite temperature effects. So all those things can be estimated as an error in this thing and find out what is left out, which is true value which is there. That's how the experiments have to be compared with. And the predicted force will be in the range of 10 to the power minus 8 newtons in our units. And at present it can be measured. It's a very, very tiny force, and it can be measured. And thanks to laser interferometry, how much is there can be actually measured, and they have done that. So I'm going to conclude the first experiment to successfully measure the Casimir energy was done in Padua in 2002. They used torsion pendulum and laser interferometry. There were conjectures that renormalized vacuum energy or the electromagnetic fields in the universe itself may account for what kind of dark energy which we talk about. Nowadays there is a dark energy which is proposed, which is nearly 75% of the whole energy of the universe, and it is responsible for the acceleration of the expansion of the universe itself. But unfortunately the numbers from this thing calculated does not match, so we cannot be too sure about it. We cannot be accounted for by this method. Now also this kind of experiment can be repeated by making sure that you don't apply Dirichlet boundary condition but Neumann boundary condition, etc., by tuning what you do with the plates themselves, and it will change the pressure, and those pressure changes can also be estimated and measured. Okay, that is what is the crucial thing about it. And it is very interesting that intuition of Ramanujan to play some role in sigma n and sigma n cube, okay, is the one which is used in all these things. And that's why I always look at Ramanujan as probably he would have made a great physicist, because that is the intuition by which many of us have been doing. Now, just for the completion, I will mention a story or mention a thing. There is this book on Dirac by Farmelo, is a person. He talks about Dirac. Dirac was an extraordinary person, and he gave theory of electron, etc., which is verified, the magnetic moment, etc. All those things worked out very well, but he didn't believe till the end the renormalization program which I described. Okay, so in 1972 or so, in that Farmelo book, not 74 or 75, there was an invitation to Professor Dirac from the former student of Balachandran. There is a person called Pierre Ramon, invited him to Florida, Gainesville, and asked him you should come and talk to the students and others which are there, as some kind of a celebration which was there. And Dirac was supposed to have responded, no, I don't want to come, I feel my life is wasted. Why? Because we are not even able to describe how an electron interacts, two electrons are interacting, And all this program of renormalization, etc., he didn't believe. He expressed it in that language, Dirac to him. But unfortunately or fortunately, this is what has been successfully experimental evidences are there for this whole program, regularization and renormalization. It has gone far beyond what Dirac could have imagined. And without that, I don't think our quantum theory phenomenology or theoretical formulations can succeed. And this is the level. And what is that intuition for renormalization, regularization is more or less similar to what Ramanujan used as a young student finishing school and college, who didn't even finish his college in Kumbakonam and Chennai here, doing in Pachabas College. That's where all the notebooks were written even before going to Cambridge. And those lost notebooks are now made by TIFR, if I'm right. The volumes are available, which is very interesting. And people have written a lot of things about it. And this is what, and without knowing anything about complex analysis. He did, because he did this even before going to Cambridge. And that is what remarkable. So what is the lesson? The lesson is we have to understand infinity and zero better. We don't know that. And we do have some idea about it. We have to understand it better. Now I want to end with a remark. Actually, I wanted to title my talk as Ramanujan, regularization and renormalization, which would have made it as 4 Rs. Unfortunately, Rajamouli has made only a movie with 3 Rs, so I stuck to only this. Secondly, today is Ramanujan's death anniversary, and the hall is also Ramanujan Auditorium, so it's better to stick to this. But Riemann himself is worried about the issues similar to things can make a difference at infinity and infinitesimal and infinitely large. He gave a fantastic talk, which is called Habilitation Talk, in 1855 in Göttingen, and Gauss was sitting in front of him. He gave the axioms of geometry at that time, where he wrote only one equation in the talk, which is ds square is equal to gij dxi dxj, summation over I and j. That is the only equation he wrote, and as way of describing any higher dimensional non-Euclidean spaces. Okay? After giving those axioms from what all those issues will follow it up, he makes some last 2 pages of remarks, extremely interesting. What will happen if the space is very, very large, infinitely large? Can this law which I have given, will it work? Or axiom, will it work? Or will it work in an infinitesimal scale of what is very, very tiny scales? Okay? And he makes a very interesting remark. If I want to see whether the space is discontinuous or continuous, or discrete or continuum, a continuum manifold, I don't know. I have given this formula, but I need a scale by which I can measure. I need an instrument to measure the distance between 2. Then only I can say it is gij, dxi, dxj for infinitesimal distances. And the distance is measured by some instrument, scale. And at that time, the only scale he knew, which he mentioned, is the wavelength of light, or light rod. He called it as light rod in that paper, in that talk. And unless we know the physics of the light rod, I won't be able to tell what is the distance between 2 things. So the physics also will change, and this I found it to be very, very remarkable, which is what we have when infinitesimal distances are involved. There is some ultraviolet behavior. We call it ultraviolet behavior in quantum field theory, which is affecting. And the second place where the thing he made is about infinitely large distance. So the law of gravity is about very large distance, force between masses, etc. Now I find whatever we know at the scale of solar system may or may not be true at galactic system, or even at infinitely large distance universe scales. People even want to talk about modified theory of gravity, etc. Or we want to know something better. So we don't understand infinity and 0. To the extent, but our understanding is becoming better and better. It is not as though our understanding is becoming better and better, and hopefully our understanding will improve. So I wanted to finish it with the references which I took. This guy Beaton Holtz is my friend. He sent a paper to me which he has given as a talk about Ramanujan. I corrected somehow this. He wanted me to correct. First he made the mistake that Ramanujan was born in Kumbakonam. It was not true. I told him it is Erode. But then there are other mistakes which are there. I corrected and he was very happy about it. And this is Ramanujan's second notebook, which is available in our library, and chapter 6. And there is a book by Kandelberger which is called Ramanujan Summation of Divergent Series. How he writes divergent series and calls some finite numbers. How did he do that? And there is some guesswork which is done by him or many other people, and that is what is explained in this book. I found it very interesting that people have to understand how to regularize and renormalize, and which was actually the intuition of Ramanujan in those days. I'll stop here. Thank you very much.
Thanks, TRG, for this fascinating talk. Any questions, please?
Okay.
I don't see any questions. We can discuss outside.
Yeah, it's very
coffee.
simple.
Yeah.
Finally, at the end of the day, it is only a historic note, and I was not expecting questions either. Okay, thank you very much.
Very much.